Hey there, everybody. It is Sean Lally, your physics teacher, coming at you again. This is our very first lesson. The first lesson is all about SI standards. Who needs them? Well, as you can see here, spoiler alert, everyone needs them. So let me tell you why. Okay, so here's a few questions I want you to think about for a couple of minutes. How tall are you? How much do you weigh? How do you know these things, and how accurate are these numbers? So think about this for just a second. If I were to ask you in the lecture hall, you'd probably tell me some things like, 6'1", 5'2", 5'1", 5'8", 6'4", 6'3". There'd be several things that would be apparent. First of all, there's a range, of course, and we're all going to fit within a certain range. It's probably going to be somewhere in between between 4'11" or 5 foot and maybe 6'6", somewhere. That's probably our likely range. The other thing that would be apparent is most people, especially if you were seeing numbers like that, you probably would have not used the units. You might have just said 6'2", 5'1", because in our culture it is basically understood that you mean 5 feet and so many inches, 6 feet and so many inches. So that's just sort of a cultural norm for us in the United States. If you were not born here, you might be more accustomed to giving a number in meters or centimeters. You might say, 160 centimeters, 1.7 meters, something to that effect. Okay, how about how much do you weigh? You might say 120, 150, 260, something like that. Again, understanding that the units in the USA would be understood as being pounds. If you were not born here or spent a lot of time overseas, you might be more accustomed to using kilograms rather than pounds. Now, how do you know these things, and how accurate are these numbers? Okay, these are really important things to think about. First of all, how do you know them? Well, you know them because somebody told you or because you measured them. Perhaps you went to a doctor's office and you were measured. They use some kind of a scale, probably the kind of scale you stand on that has a little lever system inside of it, and they slide weights across, and that basically balances you out with a little law of the lever action that you'll learn more about this semester. And you can use that to determine what your weight is according to a certain standard that we're going to talk about this evening. Or maybe you stood on an electronic balance in your home, or maybe you were weighed at an athletic weigh-in for some reason at some point in your recent past. These are all different ways you probably might know your weight. Or maybe you just had it done a couple years ago and you figured you haven't really gained or lost much since then. Same thing with your height. You probably had your height taken at maybe at a physician's office, maybe at an athletic weigh-in or something to that effect. Maybe, you got a physical. So, now, how accurate are these numbers? Indeed, what does accuracy even mean? This is not a benign question, believe it or not. So, what does accuracy mean? Well, if you said, okay, I am 5'3", and I say, well, maybe you are, maybe you're not. Let's take a look. So, in the class, I might actually measure you. You say, aha, you're not 5'3", you're 5'4", or you're 5'3.5", or you're 5'2 and 7/8, or something like that. So, you'd probably say, well, yeah, but I kind of expect that my height is sort of an approximation. And there's the rub, because in fact it is an approximation. It's an approximation in two different ways. First of all, it's an approximation in terms of the equipment that was used. How correctly calibrated is the equipment? Does it go to what fraction of an inch, let's say, or fraction of a centimeter, what fraction of whatever the standard happens to be? So that's one thing to think about. The other thing to think about is how able to use the equipment was the operator. In other words, did the person measuring your weight, they probably didn't require you to take your clothes off, so there's an additional overage because of your clothes. They probably didn't make you necessarily, well, if they're measuring your height, for example, maybe they took your shoes off, maybe they didn't, but also maybe the thing didn't go exactly through the hair on your head. So there's going to be a little bit of discrepancy because of the hair on your head if you've got hair up on your head. So point is, the extent to which these numbers are realistic or accurate is always within a certain percentage. Indeed, it would even depend on the time of day because your weight and your height fluctuate throughout the day. So to say how much you weigh or how tall you are, it's not super trivial. Now, we know in our culture there are approximate values, and we're okay with that. Give or take a fraction of an inch, give or take a pound. Nobody really cares for the most part, but it's important for you to realize that these numbers are always just approximations. And indeed, most of the things that you measure, if it's using some sort of measuring device, are indeed some level of approximation. So something to think about. And now we're going to talk about these standards, because in fact, we know that you happen to be, well, you probably know what your height is, roughly at least. And you know it in terms of a certain standard, but these standards mean something. If you know that you are 6 foot 2 inches tall, or if you are 105 pounds or 155 pounds, if you are 5 foot 1 inch tall, all these sort of things, if you are 100 centimeters tall, if you happen to be 75 kilograms, any of these things, we know that that is measured with by comparison to some standard, and we want to talk tonight about what these standards are. So this is the first of 2 videos on these standards, what these standards are all about. Okay, so let's get into the details. So, indeed, when we are measuring something, there are things that we have to consider. What are limiting factors such as our equipment? What are the assumptions that we make? That the equipment is reasonable and that it is accurate. What are the tools that we're using? How precise are these tools? How have they been calibrated recently if they are a tool that needs to be calibrated? What are the inherent types of problems with this measurement technique? Is there any sort of repeatable error or unpredictable error? Things like that. Indeed, what is a standard? So let us first talk about standards, and we're going to put these into historical context. We're going to talk about the big 3 standards, which are the standard for length, the standard for time, and the standard for mass. I'm saying mass, not weight, and there is a difference. Okay, first off, the meter. The meter is the SI standard of length. So first of all, SI. What is SI? SI stands for International System, although you notice that it is SI and not IS. Well, that's because it was originally devised in France, right around 1795. And this is the original definition. The original definition was for the meter is that it was originally 1/10 millionth of the distance from the North Pole of the Earth to the equator. So think about that, 1/10 millionth the distance from the North Pole to the equator. That's a rather strange number, and in fact, there's probably a few things that you should think about. Like, for example, did they know that the Earth was spherical? Sort of spherical. Round? Did they know that 225 years ago? When did they know that the Earth was spherical? Have we actually always known that? Well, so if you wanted to prove to somebody that the Earth was spherical, how would you do it? Let's think about this for a moment. There's actually quite a few different ways to do that. You could actually watch ships go away from shore. And if you do that, you notice at the top of the ship, let's say the crow's nest, if it happens to be a traditional ship, the crow's nest is the last part to go below the horizon. But indeed, you could also watch or look at the horizon from atop a mountain. You could watch lunar eclipses. In fact, the classic Aristotelian argument of the Earth being spherical comes from the idea that all things would gather toward a common center according to their weight, which would go the heaviest relative thing being Earth, then on top of that water, then on top of that air, then on top of that fire. I love that argument, even though it is ridiculously out of date. It's over 2,500 years old. But it's a really kind of a cool little aesthetically pleasing argument. But no matter what, humanity has accepted that the Earth has been spherical. They've accepted this since ancient times. Yes, every once in a while you read about some person a little bit misguided, maybe just a bit of a kook who thinks that the Earth is flat. But come on, folks, we all know that it is, and the evidence is overwhelming. And indeed, there is really no evidence to the contrary. Okay, here is, in fact, our home. I love that picture for lots of reasons. First of all, that's a relatively recent picture. We've only been able to take a picture like this since 1968, since we started leaving the Earth. This particular one, I think, actually was taken in either 68 or 69. I'm not sure. I like it for that reason. I like it also because it's not North America centric in the way we normally see the Earth as being North America centric, and that's Africa centric, which I think is kind of a totally different way to think about it. Okay. Now, this is a picture taken, oh my gosh, this was about a year and a half ago. I took this photograph. Notice that there is a circular shadow. That's a circular shadow. This is during a lunar eclipse. Circular shadow, that's not a straight line. That, in fact, is really great proof that the Earth is spherical, because indeed it is a shadow of the Earth falling on the moon. That was incredible proof to the ancients who understood basically what eclipses were all about. I should mention this. I have been using the word spherical a bit loosely. The Earth is actually not spherical. It's bulged a little bit around the equator, which the astronomical term for that is oblate. It's not perfectly symmetrical. The equatorial diameter is just about 40 kilometers, which is about 27 miles, longer than the polar diameter. That is to say, it's wider than it is taller, if you want to think of it that way, across the equator of the Earth versus the polar diameter of the Earth by about 27 miles. Now, excuse me, 27 miles that's most of the way from Baltimore to D.C. It's not nothing. But if you think about this in terms of the actual diameter of the Earth, well, see how this compares to a billiard ball, for example. A billiard ball, if we look at the international standards, or at least the Billiard Congress of America, every billiard ball must be cast of a particular type of resin, plastic, and measure 2 1/4 inches plus or minus 0.005 inches, which is 5.715 centimeters, plus or minus 0.127 millimeters in diameter. So, given that percentage, the Earth is actually closer to being a perfect sphere on average than a billiard ball is. You probably held a pool ball or a billiard ball in your hand before, and it feels super round. Or maybe you've held like a trackball for a computer video game or something. Then, I'm dating myself when I say trackball. But, you may have seen those before. They feel really, really round. Or maybe you've seen ball bearings or marbles, and they feel really, really round. And in fact, the Earth is actually more spherical on average than they are, which is fantastic, if you ask me. Okay, anyway, getting back to our meter as the SI standard of length. Well, that lasted for quite a few decades. You might be wondering, by the way, how do they actually measure that? I'm going to get to that a little bit later, because it was one of the classic geometry problems to measure the circumference of the Earth. It was done almost 2,500 years ago. Yes, we've known the size of the Earth for about 2,500 years. Okay. The next standard was a distance between two lines on a bar of platinum iridium, which was a basically not rustable material. That was changed in 1960 when the standard became from wavelengths of an orange-red light from a krypton-86 atom. But all of that went out the window when the standard was changed to what it currently is, and this happened in 1983. And now the standard of the meter is based on the speed of light. The speed of light, represented by the letter C. So 1 meter is now defined as the distance light travels in about 1/300 millionth of a second, or if you prefer, 1 over 299,792,458. 1/300 millionth, roughly, of a second. So that's about that distance. Let me see if you can... Yeah, imagine a yardstick's a little bit longer than that. A meter, a little over half your height, pretty much. So what that means is that the speed of light is equal to 299,792,458 meters per second, which again is about 300 million meters per second, or 3 times 10 to the 8th meters per second if you speak scientific notation. I should also point out that the letter C comes from the Latin celeritas, or for that matter, constant. Celeritas means speed, or also it's been used as C to represent that it is constant. Okay, we're going to stop there and pick up in the next video so you can get a bit of a breather, and I'll talk a little bit more about the speed of light and how fast it really is, and then we'll get into the measurements about time and mass. Okay, see you soon.